Test. Okay. Yeah, thanks for the introduction. I'm here to present the paper using client cache for font encoding, shared dictionary compression for the web, which is a collaboration between the database group at the University of Hamburg and Wollmer from the University of Oldenburg, and also backend, which is part of my ongoing PhD thesis. And to give you a bit of background, backend is a research spin-off from the same working group from the University of Hamburg. So they are interested in or use some fancy caching mechanisms to cache dynamic content in the web. So just as a bit of background. So this is of course cool because caching makes stuff faster, but at the end caching you have to fetch your data somehow, no matter what your caching is, right? So the browser has this more or less simple decision: is my the stuff that I'm looking for in my cache, or it's not in my cache, right? And if it's not in my cache, I have to load it from the server. This is of course logical, but I found that a bit sad always, because if you look at a normal website, server website in this example, you see that if you navigate through this website, for example, the website of the university, you see there are a lot of similarities, right? The header, for example, and probably the footer, which we cannot see here right now. And if you know a bit about HTML, you know that the boilerplate code underneath is most of the stuff and not really the text which you are seeing here. So maybe you could think of it instead of simple page loads, more about transitions from one state to another. So you could calculate data between these two HTML files. And if you do that, you would see that the data is actually pretty small. It's not even a tenth of the actual data of the second request. So it's a lot of wasted data for this transition. So maybe we could improve our caching so that we look for parts in our cache which we could reuse. So the general idea, and if we don't have this part, then we code the whole object. And we looked at this in a previous paper. We don't have to talk about the whole picture here. The general idea was that we analyze journeys across different websites, and always 7 steps. And the first steps were distinct page types, for example, the home page, an impressum, FHQ, or something like this. And at the end, we try to hit similar pages. For example, you navigate to a product, you get a recommendation, and you follow this recommendation, so you see similar content but different products. And what we saw was that if you hit this hot place here, where you have something in the cache which is similar, you save a lot of data. And this was compared to normal gzip on level 6, which is kind of the default in the web right now. And as you can see here, this dashed line would be broadly on compression level 11, which no one uses for dynamic content because it's just too slow. So you see there's a lot of uplift, so lower is better here, to make that clear. So this is great, but nobody is using it. So what's the problem here? Well, first of all, calculating the data is quite simple if you have both things you want to diff, but there are many problems. The first problem is that you have missing information on both sides. So you have client, and the client wants to request a product. So now if you want to calculate the data, the product has to know where this data should be calculated from, right? But it cannot know what would be actually good data because it does not know how the final page should look like. So it doesn't know how to choose the dictionary. So you could offer this, of course, to the server, because the server has more capacity, but the server on the other end does not know which source files are in the client cache. Of course, you could deploy some stateful stuff, but you will never use this because it's just too much, this does not scale really well. And even if you would track what the client has in its cache, you cannot be certain because browsers are pretty smart and they will evict stuff from the cache all the time, and you never know when this happens. So this is a problem. The next problem would be the CDN cache hit rate. So we have a CDN deployed for websites normally. So yeah, you have a distributed cache. So if you request a file and some other person has already requested this file, you will get a cache hit rate from your new server. And this is great, but if you use now this data encoding, which we had talked previously on, you have a problem because you now have up to how many files you have on your server as data per file, so n squared files, so to say, which of course lowers the cache hit rate. So for every file you could request, there are multiple versions. And yeah, you would blow up your whole CDN, and this would be kind of worthless. So you maybe would start and say, well, then let's reduce the complexity here, and we could extract a dictionary. So normal shared dictionary conversion. So you take all your HTML files, look for common strings, extract them into a dictionary, and this dictionary will then get used to calculate the data. So you have for every file which you could request, the normal file and the data. So the not so many files for your CDN to handle, and this would be all great. But the next problem here would be how big should this dictionary actually be? Because if you put too much stuff in it, it's also worthless because now you push, I don't know, a couple of gigabytes over to your client, which you will never use. So if it's too big, that's bad, but of course if it's too small, it's completely useless because there's nothing you could do. This is bad. And maybe you have a really diverse website where you need multiple dictionaries because one site may not benefit from this dictionary like another category site or something like this. And the last problem would be you have, at some point you have to cache this dictionary. And this is actually a bit problematic. You see here is a really great graphic which we talk about. The problem here is streaming, or streaming is a solution, not really a problem, but we would use this solution with this approach. Because if you would push now the dictionary and the first page load, and the first page load is an actual data through this dictionary, you would end up with kind of normal conversion at first. But of course, this dictionary would now be bigger than the normal dictionary, which would be part of this request. So you slow down your first request because you have to float more bytes. This is already bad, but it's getting even worse because you now have to download the whole dictionary before you can actually start to decode your requested file, because as you can see here, maybe you have new data and instruction which needs something from the dictionary which is at the end of the dictionary. And browsers are again pretty smart, and they will start to pass the HTML file with every byte that comes in, and maybe they see already, okay, here's a script which I have to download, so you could start, but we lose this because we now have to wait until both things are here, so we can no longer stream it and have to do the conversion first, which is again bad. And the next problem here is that this dictionary is always a gamble if you want to push it, because for example, you start here and you say, well, I want to go to the home page, and the server says, well, of course, here is the home HTML file. And now you would say, okay, we could now push this dictionary because we would not slow the browser down. The browser is maybe idling, the user is clicking on the, looking through the page and is doing nothing, so we could just push it over the dictionary. And from there on, we could use this dictionary to calculate our data for the upcoming request, which would save a lot of data, of course. But the problem here is that we never know if the user actually would use this dictionary. And if the user leaves after just one request, we now push this unnecessary data over, and maybe, depending on the kind of device, maybe on mobile or something, you put unnecessary stress or stuff like this on your mobile device, and this is wasted. And what's also important to notice that users that are just or bouncing after just one page impression are not that uncommon, because you can imagine you go through Google, you search for something, you go on a website, they go back, and so you have a lot of these users, and you will push a lot of unnecessary data, and so on. This is also bad. And maybe another approach would be, well, you could also just calculate the data from the home page, assuming that there are enough similarities between the home page and all other pages, because again, they share a lot of stuff. So no matter where you navigate, you always take the home page as your dictionary. Again, you would only have one delta per file, so this would be fine for your CDN. And yeah, it should work. But as we see in this graphic, and I don't know if you can see it here, but the blue line here is where we tested this in our previous paper. And yeah, as you can see, there's not really a great benefit. But I also have to say that this includes not only HTML files, but all text content for this journey here. So yeah, there's a bit of improvement, but not so much. So again, a bit wasted. So our idea now was that we want to introduce page type dictionaries. And the idea is quite simple, that the server could pre-decide which dictionary he wants to use, and he therefore, for example, takes all products and randomly picks one product, and this is now the dictionary. And our hypothesis was that no matter what we choose here, this should always brings a bit of a great uplift in terms of data saving. And again, we could now push this dictionary over. We don't have to do it, we could just do it. Because again, same problems as before, if we push it, we may waste data temporarily. But now, if the user gets along this tag dictionary, he could just use it as a request, as a dictionary, and then the server can just calculate the data and pushes the dictionary over. Of course, this only works if you at some point hit this dictionary, which is tagged as a dictionary. But if you do, this is great. You could also optimize here further, and for example, instead of pushing the whole dictionary, which is an actual HTML file, which is important here, not just a plain dictionary, you could also, if you, for example, have some edge computing in the cloud, in your CDN, calculate this dynamically from wherever page you were previously. And this doesn't have to be cached, this dynamic calculation, so you could dynamically calculate this dictionary while idling, and after that you have this dictionary in your cache, and this is great. You could also apply some smart approaches here to tag this dictionary, not just randomly, but you could, for example, choose something like a hot page on your website, which could be something like, which is promoted on your website, for example, a news article which people are reading, or a product which is on sale. So where you already assume that people will navigate to this. And this would have additionally the benefit that this dictionary now serves as a real HTML file. So if the user really wants to navigate to this site, he will get an instant page load because it's already part of the cache. So this has two roles. So we wanted to evaluate this, but we couldn't deploy it because there's no browser support so far. So this is on data, which is part of backend's tracking or backend's customers, and we took 1.2K HTML files across 6 websites, and these were the most requested websites or HTML files from the site. We then calculated every data within the same type. So, for example, here a homepage, a product of a certain website, and calculate every data and see what the uplift would be. For this, we used Wollmer's custom dictionaries. So, as you may know, Wollmer is a compression library which is supported by all major browsers, but only with its own dictionary. So, Wollmer uses a shared dictionary approach, but the dictionary is already part of the compression and decompression library. But you can replace it, but not in the browser. This is not supported there. But we tested this with the Wollmer library itself. And we compared this against the standard Wollmer approach. So which would be the de facto standard in the web. And these are the results. Look over here. And yeah, it's worked as we expected. Choosing an arbitrary page of the same type as the dictionary is always beneficial. As you can see here, in most cases, for example, listing pages are pretty well for this, up to 90% or something like this. Product pages are a bit worse, but still pretty great, right? Above 75%. of data saving. Of course, products work a bit worse because they have kind of unique websites, depending on the website, of course. You have an online shop with unique products, they have, of course, unique sites maybe. But if you have a specialized shop, they all share some great amount of similarities. But again, no matter what you choose, it was always nothing. And you can see it's divided across the websites that we looked at. As you can see, most of the websites performed pretty well. There was one customer with some unique sites which, of course, perform worse, as I already said. But again, still major savings, no matter how we choose the dictionary. And of course, you could go further on with the research and make a more sufficient approach to select the dictionary, because this is just random, right? With no reasoning. Okay, and lastly, we looked at the time, and as you can see, the compression time doesn't really change much. Here's a small output, so smaller is better here, right? So we saved about milliseconds on average for the compression time for the default compression level, which is of course nothing to talk about. For the higher compression levels, this is a lot. A second you could save here, but again, this is nothing you would normally use in a deployment. And for the decompression, it's again a bit faster because, of course, you have now larger chunks which you just can copy from your even smaller data. So a bit of saving here, but again, not really worth mentioning. So to come to a conclusion, data encoding is able to save most of the data for HTML files, for server-side rendered HTML files, of course. And most approaches are not feasible because, as I already said, the complexity is too high. But taking in common pages, a page-type dictionary could save, can use these computations for a dictionary, and reduce data to only one data per file, and potentially avoids pushing this useless dictionary if you won't use it. And lastly, it serves also as an actual HTML file, so you can reuse it and not just only as a dictionary. So that was it. Thanks.
Thank you, Benjamin. To be consistent, I ask for urgent questions again. There is one.
Yeah, you showed this dictionary question for HTML files, but if you look at the normal average website, it consists mostly of graphics and pictures and error.
Yes.
So is it even worth compressing it?
That's a great question, and yes, it is. Maybe I should use the microphone. Yes. The thing here is that in terms of just saving data, it's correct that the HTML file is, of course, just a small portion of it. But if you look at the greater picture, for example, in the case of backend, which provides the service for millions of users, of course, this already sums up. And even if you would maybe look at bad connection cases, for example, if you are in the train or something like that, your connection is already cutting off and stuff like this. This could be really the change if you could reduce this to a couple milliseconds, so you are able to get the HTML file and look at it, because otherwise you couldn't even use the page because of it, right? Or if you have some hotspots where the data is limited because too many connections or something like this could also make a difference. And finally, for the HTML file is, of course, the critical part for the whole loading process. So as soon as you need the HTML file to load every other stuff. So if this gets delayed, everything else gets delayed. And of course, as many studies have already shown, page loading times are really important for the satisfaction of the users. So if this takes too long, they abandon the process.
Okay, so perhaps we take everything else offline. Okay. So thank you again to all the three speakers for being in time. So this concludes today's program, enjoy dinner, and hopefully we'll see you again tomorrow at 10 when day 3 of Samsung starts.
Ja, ich war da so Hotspot für so Mobile Information System, so 20 Jahre her. Da auch so Sachen gemacht, die hatten halt ihre Informationsmodell und so weiter, das hat der ein bisschen ausgegangen gemacht. Wir haben gesagt, ich war wirklich mit dem auch uralten durch, mit so umgetragen. Ich meine, das Wichtigste ist, die erste Seite schnell. Wenn du das geschafft hast, hast du alle Zeit den Rest eigentlich im Hintergrund runtertragen zu lassen. Das ist das eine. Und das ist also statischen Zeiten, als wenn jetzt immer dynamische generiert ist, das besser ist. Also, genau. Genug sein, meine Homepage, meine Arbeitsprodukt ist ja statisch, das wird natürlich keiner Cache. Genau, die Frage ist,
bringen wir mir scientific things.
Perfekt, dann ist wieder Sinn. Genau.
Das ist sicherlich spannend.
Ich gehe jetzt schnell rauf, lege mein Zeug ab und gehe dann wieder schnell runter zum Directors. Ich will zu Team machen.
Oh ja, das ist ja gleich, ne?
Ja.
Krass.
Ja, ich finde das schon heftig, das war vom Programm, ne? Wir haben auch einen halben am Anfang. Ja. Aber vom Timing perfekt, ne? Es war genau, ich habe einen Dings laufen lassen.
Originalstunde?
Ja, genau auf den Punkt in der letzten Minute war vorbei.
Ja.
Das war halt, sind halt viele technische Details, da ist auch schon eine Frage, ne? Klar, das war mir relativ klar. Ich war schon ein bisschen gewundert, dass das niemand provoziert fühlte. Irgendwann neben mir, als du sagst, okay, dann machen wir das, und neben mir sagt einer, wir machen das. Ja. Aber sonst, so, ich war mit dem Bauer.